And we're going to continue with the next property, which is electronegativity. It is very important to not mix up electronegativity and ionization energies. This is a definition of electronegativity, and it is the ability of an atom to attract an electron to itself. So we're not talking about an atom losing electron, which is ionization energy. This is a neutral atom that wants to attract an extra electron, and effectively, if it does so, it will become a negatively charged ion or an anion. And if the nucleus is very, very attracted to the valence electron, so if I have the nucleus in the middle here, and let's say I'm going with fluorine, for example, so I'm representing the core charge, which is why it's just 1. But if you have a nucleus that is highly, highly attracted to the valence electrons, so maybe we can change the color here. So if this attractiveness is very, very strong, so strong attraction, then it is also more likely, the stronger the attraction between the valence electrons and the nucleus, the more likely that that nucleus is going to want to attract another electron to itself. So strong attractions, which mean that nucleus would want to attract an extra electron. So an electron that is not within the atom just yet, an extra electron, and that means that this particular atom, if it has a strong attraction and a strong desire to attract an extra electron as a result of that, is going to have high electronegativity, or is highly electronegative. High electronegativity, which is equivalent to saying that it is highly okay, let's try again. Electronegative. Okay, so that is electronegativity. I found this meme, I think 2 years ago, and it's just trying to show oxygen is like a junkie. Oxygen is fairly electronegative. It actually really likes electrons, so it's just trying to say that. I mean, theoretically, well, obviously, this is for funny purposes, because I don't think an oxygen atom can actually get this many extra electrons. It can only go around 2, and after that it requires way too much energy to sustain it. Anyway, let's talk about question 5. So what question 5 is trying to ask you is, if I ask you to plot a graph that shows the trend in electronegativity as you sorry, I did all that and then I realized it's in the wrong scale. So if I increase atomic number and I plot electronegativity as the vertical axis, the question is asking you what do you think the graph is going to look like. And some people say that it would just be the opposite of this, but then why is it going to be the opposite? So let's say, for example, if I have hydrogen here, would the electronegativity of helium be higher or be lower than hydrogen? And I guess you could go back and have a look at the trends across the period. So let's say, instead of talking about hydrogen, because hydrogen and helium are pretty boring, there's only 2 elements. If I have lithium here, as you go across a period, the attraction between the nucleus and the valence electrons increases, atomic radius decreases. Because there is an increase in that attraction, theoretically speaking, the electronegativity is going to increase as well. And it should decrease going down a group. So let's say maybe that's neon. And then it should go down. So lithium, going from lithium to the next element, which is sodium, the electronegativity down a group should decrease as the attraction between the nucleus and the valence electrons gets smaller. So that's an option, but I don't think anyone actually came up with this. Now, if you actually get to the next slide, so I can keep going, then you will find that this graph is actually inaccurate, and this is what the actual graph looks like. I do recommend sticking this into your book. I think I handed it out to one class and not the other. So let's try to understand what is actually going on. So there are two questions. I want you to identify which are the least electronegative elements and which are the most electronegative elements. Now, if you annotate this diagram, so you start with hydrogen, and element number 2, helium, actually has, according to this diagram anyway, close to 0 in terms of electronegativity. And then we can count, so we start with lithium here. 1, 2, 3, 4, 5, 6, 7. So fluorine is up here, and then we go down again to neon. And then I have sodium, and I have chlorine, I believe. And then we get to argon, and then we get to, if I remember correctly, potassium. Is that no, sorry, that's not potassium. That's bromine, and then we have krypton and potassium. So if you look at the trends, it's electronegativity is actually pretty interesting, because first of all, if you look across a period, if we go from lithium to fluorine anyway, across a period, generally there is an increase in electronegativity. So across a period, generally electronegativity increases. Negativity increases. However, it does stops at group 17. So fluorine is the most electronegative element. So even though electronegativity increases across a period, it goes down to 0 by the time you get to the noble gases. So the noble gases, however, have very low. So this trend breaks by the time you get to the noble gases, and they have very low, if not close to 0, electronegativity. And I guess one way to explain this is because they already have a full outer shell, so there is very little incentive to actually gain an extra electron. Very close electronegativity due to having a full outer shell. So that's the reason why the noble gases would have very low electronegativity. Across a period, sorry, down, well, that's across a period. If you go down a group, I think it does follow our original prediction, is that fluorine, chlorine, bromine. So if you go down a group, there is generally a decrease in electronegativity. Down a group, so we decrease in electronegativity. You cannot actually see this in the case of the noble gases, but I guess this is a little bit hard to see, because lithium, sodium, and potassium all have very small electronegativity, so it's fairly harder to detect a trend. But if you go from the group 17 to the halogens, fluorine, chlorine, bromine exhibit this property very well. Okay, I feel I just answered these questions. I'm just going to go through the answer. However, I think it's a very good idea for you to pause the video and try to write down an explanation before you actually check the answer. Obviously, I'm not there to police that, so this is just me encouraging to use the resources in a way that will help you the most. Okay, this is the answer. I got this straight off the textbook, I think. So down a group, the electronegativity is going to decrease, because if we're going back to our original concept, core charge stays the same, number of shells increases, so there is a decrease in the attraction between valence electrons and the nucleus. which means that it will be harder for the nucleus to attract an extra electron, therefore electronegativity decreases. If you go from left to right across a period, generally speaking, electronegativity increases because there is an increase in core charge, even though and also the number of occupied shells remain the same. I want you to always mention both the number of occupied shells and core charge in your answer. There will be an increase in the attraction between the valence electrons and the nucleus, therefore an increase in electronegativity. I would like to add to this answer, even though electronegativity increases from left to right across a period, the electronegativity, so this exclude the group 18, which are the noble gases. So the electronegativity of group 18, which are the noble gases, would be close to zero. Zero due to them having full outer shells. Okay, so if you are asked to describe the trend in electronegativity across a period, make sure you talk about the exception of the noble gases as well. Anything else? That's it. That's all for electronegativity. I'm gonna keep these annotations actually, and